Thanks. My name's Daniel Balasubramanian. I'm from Vanderbilt University, and I'm going to talk about the work our team did on a platform for satellite clusters. And there's going to be a lot of overlap with the previous talks, and we should definitely talk later. So I'm going to give a high-level overview of this platform. I also really like to get this community's feedback on our ideas and approaches. So after hearing that last talk, I'm really excited now. It seems like there's quite a bit of overlap, some similarities and some extensions and things we've done. So for the context for this is this was developed under the DARPA F6 program. So fractionated, future, free-flying, flexible spacecraft. And DARPA actually decided not to fly the mission, but this lives on as a research prototype. And there's some graduate students doing still doing some work on it. So the context for this is a little bit different than some of the other talks so far. It's about fractionated spacecraft. And just to rehash, it's an architecture where functional capabilities are distributed across multiple satellites, modules that interact through wireless links. So as you can imagine, or you may know, there's a lot of advantages for this. So distributed resources are shared. So if a camera is located on one satellite and it needs to be used by another, that can happen. It can extend the life of missions. So if a mission's flying around, technology improves, hardware improves, satellite can be dynamically added to your cluster, and you can extend the life of your mission that way. If an entire system fails, they can be replaced by a new satellite, or if just one unit of functionality fails, then there's a possibility it can be migrated to another satellite. So you have some fault tolerance built in by just redundancy and the ability to migrate or to replace entirely. And as you can guess, there are challenges. So one of those is the same as one of the advantages. Distributed shared resources. How do you not get into distributed deadlocks? How do you make sure things are secure? The communication bandwidth varies with these between the satellites and the ground. How do you make sure that the quality of service requirements requested by applications for their communications are met or even satisfiable? And one of the biggest differences, I think, in contrast to a lot of talks, is we have multiple security levels. So our assumption here is not that all the software comes from one organization. The underlying assumption is you have several different organizations that are responsible and can use this platform for their own needs. Some of them may be top secret, classified. Some of them may be unclassified. And so how do you make sure that two applications running on the platform from different organizations can't glean information from one another? So there's a multi-level security issue there. And then another big issue, how do you deploy and update software on a cluster? So it's hard enough configuring clusters to which you have access to on the ground. How do you do it when they're flying around in space? How do you make sure that the interfaces are what you expect, that the components are running, that if they fail, they can be restarted and they can be updated? And so there are two things, I guess you can say, we're asking. So one is, how do we run software on such a cluster? And two is, how do we develop software for such a cluster, such an architecture? And the solution is something we call DREMS. It stands short for a Distributed Real-Time Managed System. And it consists of two things. So a software platform, that's an OS and a middleware, and then a software toolchain for modeling applications and generating the configurations and the low-level tedious artifacts. So on the right, you can see the software platform. I'm going to go into a high-level overview about this in some details as well. So there's an operating system at the bottom, and it's implemented as extensions and restrictions to Linux. So this is research prototype. The mission never flew, but at the end, I'm going to show a little video that some of the grad students put together with some hardware in the loop, actually running our kernel and middleware and some mock-up applications. That's pretty neat. So the operating system, the OS sits at the bottom. We have a middleware sitting in user space on top of that. And we have a component-based system similar to the previous talk. And all the communication happens securely. It's supported not only by the middleware, but by the OS. So we baked into the OS there, we extended system calls and the scheduler to support these secure concepts for communication. And then we said, we have this new software platform with these new APIs, extensions, and restrictions to Linux. If we're going to get people to use this, how are we going to get them to buy into it? They got to have some sort of support. And so we said, we've had a lot of support with building graphical modeling languages. And so we have a model-driven development tool chain where you write this graphical model of your software architecture. So you define your components and their interfaces. You wire them up together visually, and then you can generate a lot of the things. It saves you a lot from writing configuration files by hand. And the second advantage to modeling, it's not just generating low-level artifacts. It gives you a framework with which to start your analysis. So for analyzing bandwidth requirements, security requirements, are the communications between two components compatible? Those questions you can answer inside this modeling framework. So I'll give a few, start with an overview of the platform, the key ideas. So this is essential for understanding the rest. But if you understand this, you understand 80% of the rest. So applications are built from something we decided to call them actors, and this is not the actor programming paradigm. Well, we just came up with a new word essentially for processes. The reason for that was actors are modeled at a high level, and they're given a persistent identifier, unlike most process models. So this actor identifier remains the same throughout the life cycle of the application, so that if an application migrates, if it goes down, if it comes back up, if it moves to another node, the system keeps the actor identifier the same, so that any other component application that is communicating with it can still find it. So actors encapsulate components. So we're going top down. So components, so my definition of component is a reusable piece of functionality with well-defined communication interfaces. That's what it means for us. And so these have well-defined interaction patterns. So we support two. We support anonymous, publish, subscribe, so DDS, and we support synchronous and asynchronous point-to-point communication as well. And the components only communicate through messaging. So there's no shared memory. There are no pipes. And this is all supported by a user space middleware library. And the middleware library is what implements the high-level communication abstractions. So the anonymous pub sub and the point-to-point. And there was a talk last year, I wasn't here at the workshop, but it was a review from NASA's Software Architecture Review Board on the Core Flight Executive. And I dug through the presentations from last year. And one of the findings was that this anonymous publish subscribe, it's a little bit different for the Core Flight Executive. So that's it's not wireless. It's just published on the same bus. But they found that it facilitates distributed development, and encapsulating functionality is a good idea. It's flexible. So it seems to be a really powerful idea, this anonymous publish subscribe, and that's facilitated by the middleware. And we also have our own component model for scheduling. So I'm not going to go into the details here about the scheduling provided by the component model, but I'm happy to talk offline. I've got lots of slides about it. And at the bottom of all this is the F6 OS. So this is where all the low-level services live, and this is where the system calls were added. System calls were added, and the C library we modified there accordingly. And as a side note, lesson learned, many of you may know it's a lot easier to change and modify kernel code than C library code. So a little bit more detail about actors. So applications can be distributed across nodes. actors can reside on the same node, or they can be split across different nodes even for the same application. And they communicate via secure messaging. So all messages are labeled with a security label. So we talked about this multi-level security. This is all assigned at design time, and we have some MAC policies of you can read up or write up or read down. So a higher level security actor can read a message from a lower level security actor, but not vice versa. So these actors encapsulate components, and they communicate either point-to-point through synchronous or asynchronous communication, or they have anonymous publish-subscribe. And this is backed in the kernel as well. So the kernel is cognizant of these security labels. So what happens is when a communication takes place, it's stamped at the actor level, and that makes it down to the middleware layer, and eventually, when it goes out the device driver in the OS. Before that happens, the security labels are checked to make sure that they're compatible between the writer and the reader. Another thing to note about actors and why we did this is in the support in the modeling language we have all the resources that are going to be required by the actor, such as the file space it's going to need, the maximum amount of memory, its priority. Those are statically declared by the developer at design time, and then the system integrator can make a decision as to whether or not it's admissible. So this modeling framework, modeling language gives us a good place to start some analysis. A little bit more about the middleware. So it's implemented in user space, excuse me, right on top of the operating system, and it's implemented using Tau, the ACE orb, and OpenDDS for anybody who's interested. So the actor interactions are call, return, and publish, subscribe. And a second thing it implements besides the communication is the software component model, the life cycle especially. So the middleware is responsible for starting components, for stopping components, for updating components, for making sure they're running, for fault tolerance. So if there's a fault manager running, it communicates with the middleware and says, I need to stop this component and bring it back up. That can happen. And so the rationale for this was that we need some layer sitting in the middle between components and the operating system that facilitates this communication, that can understand bandwidth requirements, that can make decisions about routes, can make decisions about the quality of service and which link to send communications over. And so that's where the middleware layer fits in here. So the software component model implemented by the middleware, we made some modifications to Tau. Components are essentially single-threaded. The component model has its own scheduling model. Right now it's priority FIFO, but it could be changed to earliest deadline first, or other scheduling models for the individual components of an actor. And then at the bottom we have the OS. So we call it F6 OS, F6 operating system, that provides the low-level services and resources to the actors and to the middleware. So CPU cycled, all the typical abstractions, memory, file space, network bandwidth, are all provided here. And the resource sharing, it's monitored by the OS. Security is understood by the OS. And all the interactions among the actors, the messages are based on something. The security transport mechanism is something we dubbed secure transport. So it's messaging with labels, and there's a small example of that. So I'll go through this diagram in a little bit more detail, I think. So applications are built from some number of actors, can be single actor, can be multiple actor, and actors have some number of components that communicate through the middleware that's sitting on top of the OS. And all the actors are assigned security labels at design time, and they're checked statically. We have constraint checks inside our modeling language, and the system integrator is also responsible for checking these as well. So the F6OS is part of a trusted computing base. So remember, this is designed with multiple organizations, applications coming from different organizations, not all of which may be entirely trusted. And so that's where this notion of multi-level security fits in. And so we'll say, why did we restrict the operating system? Why did we add new APIs? So we found that we needed more resource management, really needed a secure communication mechanism, and the fault management services weren't there in a lot of operating systems like we needed. So question will inevitably come up, especially with I think the next talk is Linux in space, is how are we different from Linux? So I would say that we are, it is Linux with modifications, restrictions, and extensions. So for the operating system, we added new system calls that we thought were more simpler and more restrictive. So for instance, we would restrict some of the low-level few text operations, for instance. So the low-level locking that's provided by your C library usually might not be able to utilize all the types of locks that it previously did. Another thing that we used was, since these system calls were changing in this side, we were evolving, we would spec the system calls in IDL, and then we'd generate skeleton code from that automatically, which automatically included data integrity checks and process capability checks. So instead of just writing these new system calls by hand, we'd write them in IDL, run them through an IDL compiler, would insert at runtime a process capability check that say, does this actor have the capability to use this system call? And if not, it throws an exception back up to the application. The data integrity checks are there in most system calls already, but to make sure we didn't screw things up, that applications couldn't intentionally maliciously form a bad set of data that tried to corrupt the kernel, these integrity checks were generated, checks for null pointers, checks for pointer validity mainly. We also modified the scheduler a lot. So in real-time Linux, everything maps to a certain class. In regular Linux, you have a completely fair scheduler. We use 3 different scheduling classes. And I'll talk about that in a couple slides. And the secure transport mechanism. So the kernel is aware of security labels. The middleware is included. That's another difference from Linux. We thought that oftentimes middleware has maybe a negative connotation associated with it. It's big and bloated, heavyweight. Tried to make this as lightweight as possible. And it's, again, the component model for component-based software development. So just think unit of functionality with well-defined communication interfaces. And there's always the case for reuse, and reuse is always tied to your interfaces. Okay, the scheduler modifications that we made. So we have a real-time scheduling model. Should be up front. This is not a real-time operating system, but we do have support for real-time tasks and mixed criticality systems. So the demo is going to demonstrate that just a little bit. So actors, they're declared at design time. They belong to one of 3 classes. So the system class, this is where platform actors and critical actors go. So inside that class, you have simple priority scheduling. So think of these, there's a total order here from lowest priority at best effort to highest priority in the system class. So inside the system class, there are even priority levels. And this is where the kernel critical tasks go. Anything that's been declared as a safety critical task, like a flight, cluster flight application would go there, because it's critical, has to run as soon as possible. The application class is where we have, similar to the previous talk, we have a time partitioning. So this is similar to ARINC 653 temporal partitioning, where at design time, you give a period to your actor and you give a duration. And the meaning of that is every period, seconds, my actor is going to run for a certain duration. So you have the cyclically repeating period, and the actor is guaranteed to run during that slot. And the extension that we have on top of that is that a lot of component models like the ARINC 653 restrict you to a single process per partition. We've extended it so that you can have multiple actors per partition. And we think that's pretty neat. And so inside a single partition, you can have multiple actors running, and you can make guarantees about how much time is assigned to each actor using a CPU capacity. So you can specify that within this temporal partition, if I have 2 actors assigned, they're each assigned a maximum capacity of 50%. So it's split evenly. And that's something that you can specify at design time as well. And then we also have support for lowest level class best effort. So these best effort tasks run when there are no critical tasks, when there are no temporal partitions that need to run. And this uses the Linux Completely Fair Scheduler. So we map that down to the CFS. But the time partitioning, again, is specified. It's something that's specified in your architecture model at design time. And the schedule can be automatically calculated for you as well. We have tools to do that. So I'll go into a little detail about this. So you can group actors into partitions, and each partition is temporally separated from the others. So you have firewalls among partitions. So in addition to being spatially separated, so they have their own process space and memory space, they're also not running at the same time. So you're guaranteed to get a slot of the processor's time in these temporal partitions. And so the 2 extensions, again, are multiple actors within a partition, and you can control the processor utilization of each one. And future work, we're working on this, is enabling partition scheduling on multi-processor nodes. So you're running this across SMP systems, or even multi-core systems. So here's kind of a picture of how the address space is divided. So running in user space, you might have some number of actors that are divided into temporal partitions. We go from left to right. Single actors in this temporal partition, and we have 2 actors assigned here. And then we can have a system partition that's also in user space. And a system partition would run at the highest priority level. And these are services provided, again, by the platform. So certificate managers for validating certificates, fault managers, and a net process, system and net process, an operations manager to load components, a communication resource manager to watch over quality of service and bandwidth requirements. Sorry. And then we have, in kernel space, you have partition management. So that was baked into the kernel, the scheduling, audit management, actor management, thread management. So that's a rough view of how the system is laid out. So the communication. So among other restrictions we made, so we disabled BSD sockets. So it's like Linux, but you can't just say, open a socket and I want to just send a request out. So regular actors can't initiate or configure the network communications. So this is all pre-configured by the platform. So your communication is handed to you. So think of it as the phone lines are already there. You can't establish new lines yourself between actors. So you can still use the socket-like communication APIs with security labels, and we have timestamping at the IP datagram level. And the reason for this, the second one, was actually a late use case that came up that said, well, we'll still probably need to get to ground systems and access systems that aren't aware of the secure transport mechanisms. What do we do there? So we extended it a little bit. Originally, the idea was you communicate only within an F6 network using these trusted security mechanisms. And all messages, they're stamped with a security label, and they have to obey some MAC policies. And again, that's you can write up or read down. So here's graphically kind of what it looks like. So it enforces these 2 rules, secure transport. So an actor A wants to send a message to actor B. So the first thing it does, it only writes messages to endpoints. And endpoints and flows are configured only by the trusted platform actors, and they're used by the regular actors. So this flow has to exist, and it can't be configured by A. And what actor A does when it wants to send this message M over to B is it writes it to the endpoint. The kernel determines if there's a suitable flow from A to B. It picks the best one. There can exist multiple ones. So in this way, routes can be dynamically reconfigured if they go down. The kernel also checks that the security labels are compatible so that actor A can write to actor B. So all the endpoints have labels as well. And then it's also checked on the receiving side. So when actor B receives this message, the kernel also enforces that the security labels are compatible. Okay, so quickly about the modeling environment. So we said that a new API, a new operating system, and middleware, how are people going to be able to configure and use this thing? It's hard enough just to write things, but then to configure the platform. So we went with a model-driven development approach for just modeling the system architecture. I know in some circles, modeling can have a bad connotation associated with it too. But this is, again, a lightweight way just to model the architecture of the system. And we believe it, in addition just to being user-friendly, also gives you a good place to start your analysis. So the designer creates architecture models for their actors and components and interactions. So time constraints didn't let me go through the entire modeling language, but I'll summarize it and say you define your components, you assign those to actors, you state your actors' resource requirements, you configure the interfaces of your components, you connect them if they're point-to-point. Otherwise, anonymous publish subscribe interfaces. I had a conversation before the talk about how do you make sure that the pub-sub interfaces line up, that a component that wants to subscribe to messages is indeed subscribing to what it thinks it is and not listening to nothing, that the publish and subscribe are going to the same place. One is listening to what the other one is saying. And that's handled in large part by static guarantees in the modeling environment. So all the data types and the interfaces are defined inside the model, so you can be assured that the pub-sub interfaces are going to line up. There's not going to be a mismatch there. So the ultimate result of all of this is platform configuration files and analysis framework files for configuring. So you get this platform configuration file that describes your components, describes your actors, and it tells the operating system things like, here are the actor IDs, here are the security labels that these actors understand, here are the communication flows that you need to establish before the components are started. So the rationale behind this was software platform it's flexible, it's powerful, but developers are going to need tools to use it. And we're going to need a way to analyze these resource requirements, especially of actors, and the security requirements as well. So we have a label checking library integrated into the modeling environment to do static checks on that, to check at design time that the labels are compatible as well. System integration is also facilitated through the modeling environment. So the system integrator receives applications and models from the developers and then rebuilds the applications with trusted libraries. So that's over here. So the application developer gives them this. The components that they develop this in their favorite IDE, these are C++ components. They give the metadata in the form of the models, and then the system integrator uses those to rebuild the applications and the software bundle for the platform. Validates it, and then comes up with a deployment package that's then shipped off. It's got metadata describing the components and the architecture, and then the actual executable binaries. Those are uploaded to the trusted platform actors that then are responsible for loading the components, for reading the metadata, and then loading the binaries. So, and the rationale behind this is that you really need a trusted entity to perform the final verification, the checkout, and just make sure things fit together, that security requirements are met, that resource requirements are met. And then deployment is handled by a platform actor we call the deployment manager. So a cluster operator approves the suite and authorizes the deployment. And then from the ground, they can upload this plan to a trusted platform actor, and then distributes the components across the nodes, sets up the resources, sets up the labels, sets up the communication links, and starts all the actors. So I don't have a diagram describing the component startup process, but we also have a similar set of states that components go through. So we call them things like components can be passivated, so they're brought up, but they're not transmitting. They might be listening on pub-sub interfaces, and then they're activated. They can be stopped, and they can be started. And the rationale for this deployment approach was that we thought that the ground system should be built using the same software, just for homogeneity. So the demo, this describes the topology. I think it's readable. So the demo is 3 nodes. So the 3 hardware nodes are the black boxes, and those are IBX boxes. They run an Intel Atom processor, x86. And those are similar when the mission was still planned. Those were similar to what we thought the target hardware might be, something like that, the same order of processing power. So those represent the satellites, and those are connected. Let's use this. Those are connected via a secure internal network that understands their secure transport mechanism, and they're also all connected to the orbiter flight simulator. So it's a piece of software that accurately simulates space flight physics. And then one satellite is connected to the development machine that's through the ground link. So the development happens here. Applications are deployed onto here, uploaded here, and then the deployment manager here is responsible for distributing the actors and the components across these links. And then for demonstration purposes, this mock-up application uses this so you can get a visual view of where the satellites are flying around. So I have to switch over to that. Okay, I'll pause this as I go along. So this is the modeling tool. This is exactly what it looks like. Don't get lost in the details, so I'll just give a high-level overview of it. It's called the Generic Modeling Environment, GME, and it was developed at Vanderbilt. It's been around for about 20 years. So it's a graphical modeling language, and in this case, again, it's for defining the architecture of the system. So this diagram, I often describe it to my wife as drawing boxes and lines. So we've got boxes and lines, and in this case, these boxes and lines represent the components of actors. So we have the component definitions here for a cluster flight application and for an image processing application. So those satellites I showed, they're going to run this mock-up demo scenario runs two applications. Each satellite's running a cluster flight application, and it's running an image processing data, CPU-intensive image processing application. So you can see that these components, these little ports inside them represent the interfaces. So those are the communication interfaces. So it's kind of hard to see here, but the difference in the shape represents, is it a point-to-point interface, or is it anonymous publish-subscribe? So those are defined. Let it progress a little bit. And then the screenshot shows how the components are wired together. So if they use point-to-point communication, we just connect these interfaces. It's as simple as that. And that states eventually that what that does is it writes a configuration file out that tells to the operating system and to the middleware there exists a network flow between these components. Configure that for me and assign it certain security labels. So rather than writing all of that metadata by hand, it's written here and generated for you. So the point-to-point interfaces are connected here. Just lines between the components, ports of the components. Goes a little bit further. And here's how components are assigned to actors. So actors are really the unit of scheduling for the operating system. And in this case, we're going to temporally partition some of them, and some of them are going to be critical tasks. So the image processing application is going to be temporally partitioned because it's not critical, just needs to run at a certain rate. In the cluster flight application, 3 of the actors respond to emergency commands, critical commands. They'll go in the system partition, and the last actor for the cluster flight application will just be temporally partitioned. So how does that work? So this goes along a little bit. Okay, so here's how network, the network is configured in the modeling language. So these boxes here represent the satellites. And these are the network interfaces. So this is connected to the ground network, satellite 1, satellite 2, 3. They're all connected to the internal secure transport network. And it's hard to see here, but these are the IP addresses that are assigned to the nodes. So that configuration also goes here. It's IPv6 addresses. So we're trying to future-proof ourselves for future missions, even though nobody down here, very few things use IPv6. We're ready to handle IPv6. And the network itself is also assigned a security label there, you can see at the bottom. Here's how the schedules are assigned to nodes. So it's as simple as, again, connecting lines between elements. So we have these partitions, and they're assigned to schedules, and the schedules are assigned onto nodes. So I know this is highly abstracted, but what you're seeing here is that we think it's a really straightforward way to configure applications. I'll try not to pause anymore. Okay, so here's our node deployment manager running on the ground. So this is kind of sped up. We're giving the command to distribute this plan, distribute the binaries and the metadata to the cluster. And the log messages that are flying across the screen are saying things like, I'm starting the nodes, I'm uploading the plan, and here's what it looks like in orbiter. So here's the satellites flying around. And what's going to happen is they're going to receive a scatter command. So that's one of the critical commands to which they're supposed to respond. And when that happens, they're supposed to simultaneously activate their thrusters and fly away to a safe distance. So the grad students did a good job setting this up and integrated this with orbiter. So what happens is the ground station is about to send that command to the cluster leader over the ground network up to the satellites. And when it receives it, it's going to pass it along. And there you can see the satellites flew away. There's a view of it. You can see here it received the scatter command. So orbiter is just echoing the current status of the satellites, and we're actually running on those IBX hardware boxes. And here are the log messages flying along. And in a couple seconds, you'll see one. I think it'll be there's a red box around it that shows that they received the scatter command. So we have verbose logging enabled here as well. And here it comes. Yeah. So there's red boxes. The satellites received the scatter command, and so that's what caused the change in the orbiter simulation you just saw. So with that, here are links to a bunch of extra references, and again, I'm excited and happy to talk to people about this and get feedback.
Very good. Are there questions? Wow.
So I just wanted to ask you, out of GME, are you actually generating your IDL code for the components? And are you still specifying your components according to the Corba component specification?
It's modified, but it's a modified version. But in short, the answer is yes. So IDL is generated. So there's I glossed over that. So in addition to platform configuration, the data types, for instance, that we use to configure the publish subscribe ports and the point-to-point ports, that IDL describing those data types is can be specified in GME, and it's also automatically generated, and it's syntactically, and it's checked for syntactic correctness there as well.
Ken Peters, JPL. Obviously, there's a lot of interesting questions about the security and how you guard against bad actors that have been maliciously coded. But just to pick one out, have you, particularly since in a lot of our applications, the selection of CPUs is pretty limited, have you documented any capacities that the CPU must either provide or must not provide in order to support this system?
So for the temporally partitioned actors, there's a schedule calculator that runs, so it can be automatically generated. And if that is assignable, if it can generate a schedule, then it's safe. But there's no protection against a runaway process that just something that runs in the critical space that hogs the processor. So there's nothing against that.
Okay, but also things like memory management units, or preventing cache snooping, or stuff like that.
Yes. So in our design discussions, cache snooping was one thing. And it's disabled now, but we can enable it in the kernel so that when processes are swapped, cache is cleared. But we don't do that now, but that did come up in design discussions. Covert channel analysis was initially a big part of this project as well.
I was interested in your patterns, and I wanted to find out if you could characterize the nature of those patterns in your pattern matching process, and what are the benefits of using the patterns as opposed to a more conventional technique?
The communication patterns? So anonymous publish subscribe, I think, is really powerful. So there was the findings from the architecture review board said that this was really made things flexible. One of the talks yesterday, I think the reason it made it easy to just plop in the compression there was because of the anonymous publish subscribe. You don't know, the writer doesn't know who's subscribing and doesn't need to know or doesn't want to know. So that's a powerful communication abstraction. Whether or not point-to-point is required is, we think it's useful, but it may turn out that it's not. So if that's feedback we get from the community, then that's valuable for us as well. But as opposed to just using general sockets, it was just not secure enough.
We have time for one more.
Hi, Daniel. Brendan O'Connor from Emergent. Just a caveat, I've used Daniel's system, an early version of the system. I think it's great. I think it's a really powerful tool for developing flight software. I have a question. It really kind of looks like what the future operating systems look like. And it looks like the Kerbals are using it on their space program. Is that right?
I'm sorry? Can you?
The Kerbals. You had the Kerbals up there using.
Oh, yeah.
So my question is about the deployment manager. Does the deployment manager control configurations? And does it also handle things like availability? If one component goes down or a node goes bad, will it deploy components on other nodes?
So there's a fault manager actor that runs. That's responsible for collecting fault information and telling the deployment manager that a node needs to be actor needs to be restarted, either restarted or possibly migrated to another node. So the particular reaction to the failure is determined by the fault manager, and then the deployment manager is responsible for the restarting or migrating it.
And what about like warm and hot backups? Does it handle that as well? Is that the deployment manager's job?
So it depends. We had these during design, similar discussions during design meetings about how much state to store. And that's something that's, we don't have a definitive answer. So we could support that. The amount of how much we store is, it can change. How much we checkpointing data, for instance.
Okay, my last question is, where are you in your development? Are you ready to fly? Somewhere short of
so
that?
we think this is technical readiness level, maybe level 4. So we count the IBX boxes as our breadboard, according to the official scale.
I'm interested in, you mentioned that you have the ability to have multiple processes running in a single time partition.
Mm-hmm.
What's the use case for that? Like, I mean, the idea of going to a process model is that you have a multi-threaded process running in a single partition. What's the use case for having multiple multi-threaded processes in a single partition?
Right. So if these actors or processes are tightly coupled, then that's one use case. So the CPU capacity attribute that we put on there guarantees that one doesn't just run away with it. But it's the use case we thought it was when they're really tightly coupled.
Okay, very good. Thank you. I think instead of taking a break, we've had one just a little while ago.